Hello everyone. I'm going to talk about offline reinforcement learning. In this talk, I'm going to focus on using function approximation for reinforcement learning. But since this is the last talk of this workshop, so unlike what Chaba did in the morning, I'm not going to tell you any negative results. Mostly, I'm only going to tell you about positive results, so that when the workshop is over, when we get back home, we still feel optimistic about working on reinforcement learning. All right. So this is a joint work with two Cornell students, Masatoshi and Jonathan. All right, so in the past decade, we have seen many successful stories, exciting stories about reinforcement learning practice. We use RL techniques to solve these extremely challenging games such as Go and video games. And recently, we can even use RL to train policies to manipulate a very complicated object and actually train a policy better than traditional methods like optimal control or motion planning could do on this robot manipulation. I think one of the lessons we can learn from these successful stories is that when we combine reinforcement learning together with rich function approximation, and under the situation where we have a lot of training data, for instance, in the simulations, we can often find a very good policy, policies that are better that we can hand engineer. So this is the typical pipeline for online reinforcement learning. So as you can see here, there's a closed loop. We have an RL component where it computes policies to interact with the real world. In this case, it's a robot arm trying to manipulate the ball. And then when the policy interacts with the environment, it generates data. And then the reinforcement learning agent will access this data set and try to refine the policy. And then this process goes on for many, many, many iterations until we are satisfied about the performance of the policy. So online reinforcement learning is a very popular setting. It's very challenging setting as well. I personally also spend a lot of time thinking about online reinforcement learning. But I think there are several issues about this setting. I think, first of all, the learning could be very slow at the beginning, especially at the very beginning, we don't have enough data, and we sort of have to do very smart exploration to collect very useful and diverse data. And then we ultimately have to do some exploration. We have to do some sort of random exploration in this process. But sometimes it's questionable, whether random exploration is actually safe or not, right? For those safety critical applications like autonomous driving, for instance. So different from online reinforcement learning. So the offline reinforcement learning paradigm works like this. As you can see here, there's no closed loop anymore. We only have a static data set, which is collected by some behavior policy, pi subscript b. So this policy could be, in this case, for instance, some policy where students used to control this robot to do different kind of task, maybe similar task, but not exactly the same, right? So we have a lot of log data about this robot interacting with different kind of objects, for instance. And in this offline reinforcement learning paradigm, we only want to use this static data set to directly learn a policy pi that can work well on the task that we care about today. And once we learn that policy, we want to directly deploy that policy in the real world. Right? So we don't want to do any exploration in this case. We don't want to do any online interaction. So the benefit of this framework could be that we will be able to leverage a huge offline data set. And then we don't have to do any online exploration. So this might be more suitable for applications where safety is important. What are the potential applications for offline reinforcement learning? So I think the first application is robotics. So this is the work from, I think, Google, where they build a robot farm, where they just deploy these robots and let them do sort of random interactions with the objects in this bin. They let the robot do this interaction in a 24x7 fashion. They collected a huge offline data. And then at the end, they try to train a policy using this large offline data to sort of learn how to pick and place objects from this bin. And another application is autonomous driving, where human drivers could contribute a lot of data. But in this kind of cases, if you want to do random exploration in real world, it might be a little bit dangerous, right? And then I think the third application, which I personally really like it, is this blue navigation example. So in this recent Nature paper, where they use offline reinforcement learning methods to learn a policy to navigate this broom. So the goal here is to learn a control policy for this broom so that it can stay in the predefined position, and also sort of by leveraging sort of the wind field to minimize the total energy cost. Right? And the offline data here is the pre-logged data from some sort of handcrafted feature before. And of course, there are a lot of other applications in healthcare. I'm not the expert in this area, but there is a very nice offline reinforcement learning survey paper from Berkeley where they talk a lot about this potential healthcare applications. All right, so hopefully I convinced you that offline reinforcement learning is interesting, but offline reinforcement learning is also challenging. And in order to see that, let's contrast it against the traditional supervised learning, for instance. So in traditional supervised learning setting, we have a huge offline sort of static data set as well. So in this case, just data sets about image and their labels. And we train a model, we train a nonlinear function approximator as a classifier. And once we have that, we can deploy them, we can deploy these functions in real world and test it on examples that we probably haven't seen in the training time. Right? So in traditional supervised learning setting, we often assume that the training distribution is equal to the test distribution. But this is not really going to be true in offline reinforcement learning setting, where we're going to face some distribution shift. So let's consider this example of learning to drive from expert demonstrations. So I have a huge offline data set that consists of expert demonstrations about driving the car, right? And I will learn a policy that maps from state to actions, in this case, maybe the steering angle. And then once I learn the policy, I want to deploy that, right? But when I deploy that, I will actually use my own policy to drive the car, right? I will actually make predictions on the states that will be generated by my policy rather than the expert policy in that case, right? So it might look like that, because the learning process is not perfect, you're going to make some mistakes along the way, and then mistakes compound, and eventually you get to a region where you don't have any training data in this case. Okay, so this is different from the traditional supervised learning setting. Okay, so in this talk, we're going to focus on answering this question: how should we tackle offline reinforcement learning? What are the settings? What are the goals? And specifically for the setting where the offline data does not have sufficient coverage. So in terms of outline, first I will talk about what are the goals that we potentially want to achieve in offline reinforcement learning. And then we will talk about an algorithm that sort of achieve this goal. And in the last part of this talk, I will switch to a slightly different setting called imitation learning or inverse reinforcement learning, where you don't have reward signals anymore, but you may have some high quality demonstrations together with a large offline data set. Okay, so the model we're going to stick to is the finite horizon Markov decision process. I think you have seen this setting multiple times, but let me just spend 20 seconds on that so that we can be on the same page in terms of notations, right? So we will have pi to denote policy. The policy maps from state to actions. And once the environment receives an action, it will output a reward signal, and it also outputs the next state, which is sampled from the unknown Markovian transition P star. In finite horizon setting, this process repeats for capital H many steps. And your goal is to find a policy pi that maximizes the expected total reward across capital H many steps. That is our goal. And for offline reinforcement learning, before we start doing learning, there is this process of collecting offline data. So in this case, we assume that we have some behavior policy, pi subscript b, which has already interacted with the environment for many, many rounds. And I'm going to use this notation D superscript pi to denote the state action distribution induced by policy pi. Right? You can think about this as the average, state action distribution induced by the policy pi over this capital H many steps. We're going to assume that we have an offline data set that is in the format of state action next state triples, where the state action pairs are sampled from this state action distribution induced by the behavior policy. And the next state S prime is sampled from the unknown Markovian transition conditional on the state action pair SA. And for simplicity, let's assume these data triples, they are ID sampled. That is my offline data. I forgot one thing. In the data set, we should also have, so throughout this talk, I'm going to assume that the rewarder function is known. So I'm not going to spend time and effort on learning the rewarder function. Yes.
Do we know the behavior of both state?
We don't. Yeah. So particularly, we don't know, for instance, what is the probability of taking this action A under the given state S? We don't have these numbers.
Yes, something.
Yeah, we will assume something about that. Yeah.
Yeah, but we observe like sample paths or just the triples?
Yeah, so for this talk, just triples. But if you have sample trajectories, maybe for maintaining ID assumptions, you just for each trajectory, just take a triple, randomly sample a triple and throw away the rest, and take the next ID trajectory, repeat the same. Or if you know, your Markov chain mix very fast, then maybe you can select these triples based on the intervals. This ID assumption.
So does it, the question on follow-up on that, like, do we know, if you know the policy, then would it help?
If you know the policy pi b.
The policy pi b, would it help?
Maybe. I think if you know the probability of getting this action A under this S, you might be able to use some importance weighting techniques. But for reinforcement learning, unlike mandate, if you do importance weighting, you might get into this exponential sort of curse of horizontalization, right? Okay, so as I said, we will focus on the setting where the offline distribution does not have sufficient coverage. So let me simplify this problem. So in this x-axis, let's use this x-axis to represent the state action space. So I have a distribution that looks like that. This is the distribution over state action pairs induced by my offline distribution, offline policy. So in the worst case, my globally optimal policy pi stars distribution might be somewhere here, which does not overlap with the offline distribution at all. So in this case, there seems very little hope that we can aim to find this global optimal policy pi star, right? After all, we don't have any data on the part of the state space where the optimal policy is going to visit. So we really don't know what's going to happen in those regions. But maybe we can focus on searching over high quality policies that are potentially covered by the offline distribution. So in this case, I may have pi 1, pi 2, pi 3. They are all covered by the offline distribution. And in this case, I might just want to find the best one among them. Right? I'm not going to aim for finding the globally optimal policy in this case, but I'm going to aim to find the best one that is covered by the offline data. Right, so let's look at this particular simple example. This is a binary tree. Everything is deterministic transition. I have rewards 0 everywhere on this tree except the 2 leaf nodes. I have reward 0.9 on state 10. I have reward 1 on state 15, 0 everywhere, right? So obviously the optimal path goes along this direction, right? The optimal path will pick reward 1. But let's see, in this case, my offline distribution just covers the other subtree, the left subtree in this case. So there's literally no hope for me to identify the optimal path because I don't even know what's going to happen, what the transition is going to look like under this right subtree, right? Because I don't have any sort of evidence in that part. But maybe in this case, what we can hope for is to actually identify this policy, the policy that is not the globally optimal, that is not globally optimal, but is high quality, is reasonably good. So this is hopefully doable. All right, so our goal here is to basically compete against the best policy that could be covered by the offline data. So I will define the coverage mathematically in a few slides. Okay, so another thing we want to achieve in offline reinforcement learning, especially when we apply this to large-scale MDPs, is the generalization. So in supervised learning, as I said, we use rich function approximators to achieve generalization in the sense that we want to make good predictions on the examples that we don't see in the training time. Right? And mathematically, what we want is that our pack sample complexity guarantee only depends on the statistical complexities of the function class that I'm using. For instance, in this case, could be VC dimension, random marker complexity, or other complexity measures, right? And particularly, I don't want my sample complexity bound to depend on, for instance, in this case, total number of unique cat or dog images in this world, right? That's just not possible. And we want similar things in offline reinforcement learning and in general reinforcement learning as well. Because when we apply, reinforcement learning techniques to games like Go, we know that the total number of unique border positions in this case is larger than total number of atoms in the universe. So there's no hope for us to sort of enumerate all possible border positions and trying to memorize, the optimal strategy there, right? So we have to be able to generalize. We have to make good predictions, even on those border positions that we haven't seen during the training time. So mathematically, we want to identify high quality policy with number of samples scaling polynomially with respect to the statistical complexities of some function class that we're going to use. Okay. So in summary, the key questions are, in offline reinforcement learning, can we design an algorithm that can find a policy to compete against the best policy among those covered by the offline data? And simultaneously, can we achieve this goal with number of offline samples scaling polynomially with respect to the statistical complexities of the function class that we picked? All right, so now let's talk about some specific setting and algorithm. So different from what Java talked about in the morning, I'm not going to design function class to capture sort of the Q function. I'm going to do a model-based approach. So remember, we had this unknown Markovian transition. So in this case, this potentially could be a stochastic dynamics that models this car, for instance. Right? So this is an unknown. So in the model-based approach setting, we want to use function class to capture this guy. So I may have a family of functions. Each of them takes a state action pair as input and maps to a distribution over the next state. Right? So think about each function here as sort of a conditional generative model, which takes the state action pair as input and try to build a distribution over the state from where we sample the next state. And we're going to assume that this function class is rich, such that there exists a function that can perfectly capture the ground truth unknown model. Okay. This is a typical realizability assumption in supervised learning. Potentially, we can relax it to organostic learning setting, but I'm not really going to talk about this today. And in terms of computation, let's assume that we have access to some black box planning oracle, and an oracle that takes a Markovian transition P as input and a reward function as input, and outputs a policy that maximizes the reward. So this is really a computation oracle. So let's look at a very naive approach. So I think in control, this is often called certainty equivalence. What we're going to do is just take the offline data and trying to find a model from the model class, from the function class, that fits the data best. Particularly, let's do maximal likelihood estimation. In this case, I'm going to find a model that achieves the maximum likelihood of the data. Once I train this model, let's just pretend that this is the ground truth model. Let's call our black box planner to compute the optimal policy, right? I'm just treating p hat as if it were the ground truth transition. Then I input the reward function to this black box planner, and this guy outputs a policy. And maybe let's just apply this policy in the real world and see how it goes. So when the offline data is not diverse enough, this approach could generate terrible policies, right? So let's look at this binary tree example. Again, remember we have reward 0 everywhere except 2 nodes, right? I think node 10 has reward 0.9, node 15 has reward 1. And we only have offline data on the left subtree. So in this case, our model p hat could be arbitrarily run in the right subtree, right? Particularly, maybe I will make completely wrong prediction at the node 3. So in this case, maybe my model believes that if you take the left action at node 3, you would be translated to the right subtree rooted at node 7. And if you take an action, the right action, you would be routed to the left subtree rooted at node 6. Right, so our model actually believes something that is completely different from the ground truth model. And in this case, if this planner will pick a policy that looks like right, left, right, because the planner believes that if you pick this policy, you would achieve reward 1 in the model p hat. But the reality is that if you execute this policy in the real world, you will actually just visit a state where you have reward 0. You're even going to miss the suboptimal policy inside this green region. So that's the issue of this naive approach. Now, this naive approach could work really well if you have very diverse offline data, right? If the offline data covers everywhere, then this is a very reasonable model. And this is a model people actually sometimes use in practice too.
So why is it that if you have no data about the right-hand side, the p hat tells you?
Oh, just an example. Basically, I was just saying you don't know what p hat would do at the regions where you don't have offline data.
Right. I was just thinking maybe the more natural thing is just to be assuming everything is 0 on the right-hand side because you don't have any information about it.
Yeah, so I would think about this as you just look at the models which all have training error equal to 0 and just pick one model, right? Because at that point, you don't know which one is actually better than the other ones, right? And you haven't picked this one, for instance. Yep.
Does your data have to be draw ID from the fixed policy? Because this figure seems like it also works even in different policies.
Yeah. So I think when I say the offline distribution, you could think about this as just maybe let's say a distribution over state action pair. It may not be even a valid state action distribution induced by a policy.
Okay.
Okay, so let's look at a slightly different approach, which is pretty much the same as the previous one, except that I'm going to add a little bit constraint in this case. So the first step is the same. I'm going to train maximal likelihood estimator. I'm going to find a model that makes the data as likely as possible. And once I have this model, I'm going to do this constraint optimization. All right, let's forget about the maximum objective for a second, and let's look at the constraint. So what this constraint is saying that I'm only going to focus on the models which is close to the maximum likelihood estimator under the total variation distance averaged over the training data set. So here delta is some threshold, right? So picture-wise, I have this constrained ball, which is centered around the maximum likelihood estimator, and I'm only going to look for models inside this ball. Right, so the intuition behind this is that I will know, if I set delta properly, I will know that the ground truth model P star lives somewhere inside this ball, even though I don't know where it is, right? So this total variation distance might look a little bit complicated from a computation perspective, but you can easily replace this by sort of a likelihood-based constraint, right? Where you say, basically, I'm only going to look at models whose empirical log likelihood is not falling too below of the empirical log likelihood of the MLE. Yeah.
How do we set delta in a particular? Can it be the case like in the previous example? How do we have two subtrees? So essentially, the delta will be really high because for example, they have no idea.
Yeah. So delta will be set exactly as the generalization round of MLE. Because I only want to make sure, I only need to make sure that P star falls into this constraint. I want to make sure P star is a feasible solution of this guy. So delta is exactly the generalization bound of maximum likelihood estimate. Okay, so once I have this constraint, I will do this max min optimization. So basically this says that for every policy pi, I'm only going to compute the conservative estimation of the policy value by selecting the least favorable model among the models in this constraint set. Right. Once I have this pessimistic or whatever conservative estimation of the policy's value for every policy, I'm just going to select the policy that has the highest conservative estimation. That's what this max min is doing. So now let's talk about the coverage before we talk about the sample complexity of this approach. I've been talking about coverage sort of in high level setting. Now let's define the coverage in this case. So I'm going to use both the distributions, policy-induced distributions, and the function class to define this coverage. So in the numerator, I have the state action distribution induced from a policy pi that I'm interested. And in the denominator, I have the state action distribution induced by the behavior policy. I'm looking at this ratio. And inside the expectation, it's just the total variation distance between a particular model P prime and the ground truth P star. So I'm looking at the ratio between model errors, right? And then taking superior in front of this guy. So this is my density. This is my sort of coverage definition. I will say that a policy pi is covered if this quantity is bounded below infinite. So this looks a little bit complicated. Let's look at two special cases and try to get some intuition of this quantity. So the first case is that you can always show that this quantity is upper bounded by the worst density ratio between these two distributions. That's not hard to see. And this density ratio based coverage is a well-defined quantity, is a commonly used quantity in reinforcement learning literature. And another extreme case is that this is not going to be realistic, but imagine that somehow you know a lot of prior knowledge about the system, and you just design a function class where every function in the function class looks the same as the ground truth one. Right? So in this case, you don't have any model error. So regardless of whether the two distributions are going to have overlap or not, it doesn't really matter. This quantity is going to be equal to 1. Right? So in some sense, this quantity takes both the distribution and also the function class power into consideration. Okay, so this is what the guarantee we're going to have from that previous constraint optimization approach. So particularly, given n ID offline data triples, with high probability, we can find a policy pi hat that can compete against any policy pi star, not necessarily the globally optimal, but any policy, right? As long as it is covered by the offline data, meaning that this coverage C is bounded below positive infinite. This is the robustness that we were talking about. We want to actually compete against any policy that is covered by the offline data. And we also have this statistical complexity of our model class. So in this case, for simplicity, I'm just assuming that my function class is discrete, contains finite number of functions. So typically in this case, the natural statistical complexity is just the log of the size of the function class, right? And particularly here in this bound, I don't have explicit polynomial dependence on the number of state and action pairs in this case, right? Everything is hiding inside this complexity of the function class. This is the supervised learning style generalization bound we were talking about. Right, so as you can see here, when you do things in model-based perspective, all we need is actually just a coverage and also just realizability, which contradicts to what Chaba talked about in the morning, right? Where in the value function approximation perspective, just being realizability is actually not enough. This is actually just being realizability in the Q function is also actually not enough in the offline reinforcement learning setting. Okay, so
Reach the time frame.
Yes.
I'm just wondering, why is it h squared? Because if you time horizon is h, You can use that most constant every time. So shouldn't the worst case be over each?
I think because there is actual steps and also the total reward in this case, the trajectory-wise reward could be capital H. So I think that's why we get the H here. So if you assume like trajectory reward is bounded between 0 and 1, you just get 1 H, I think.
Yeah.
If you're going into that, is this graph dependence of H optimally?
Probably not, I don't know.
I would think it's H to the 1/2.
H to the 1/2. Yeah, so this, if you instantiate this result to, let's see, tabular MDP, this is definitely not optimal. Yeah. And in fact, you will get, I think, a linear S in this case. You would expect to get a square of the S.
I was going to ask the same question as me. So, but by the way, the algorithm is like having constraint for each P. So yeah, I don't need to think about hypothesis testing perspective. I mean, these are like sequence of things. So I don't know if taking that into account. Oh no, sorry, it's not. You don't assume that like the trajectory of the observer. So okay, never mind.
Yeah, so this is interesting. I was just thinking, can I understand this really as a pattern or some kind of optimization problem with unknown parameters, which just happen to be the MDP? Can I understand that?
Sure. Yeah, I think it makes sense. Yeah.
In principle, you can ask the same question for any optimization problem and unknown parameters.
Yeah.
But in your problem, you have.
I guess here the only difference is that you really have to consider this coverage concept. But you have to look at the distribution shift.
So and also clarification, the MDP is infinite horizon or finite horizon?
Capital H.
Oh yeah, sorry. Finite.
Why is there no dependence on the size of the rewards?
Size of the reward?
Yeah,
What do you mean by size of the reward? Number of state and number of action there?
like the magnitudes of the rewards.
Oh yeah. So I think this is hidden in one of the H. So we just assume that the total trajectory, like every time step, the reward is bounded between 0 and 1. So RSA is between 0 and 1.
Okay.
Then RSA is known. So you don't learn that.
Okay. Maybe this is stupid, but maybe just as it's come over time. Like, why isn't the regret kind of just naively bounded above by each? Because any policy has its reward between 0 and each.
Yeah, I think you really have to look at compounding errors. It's not just like summing every time step up.
Isn't the reward just summing or?
Okay.
Yeah, I don't even know if in intended case you can just choose linear H.
It might get H, but it's A, but you may not have H divided by root n.
This is less than it. Oh, the thing multiplying it is less than 1.
Yeah, you don't go back to those good notes.
Oh, that's the, yeah. So this quantity could be less than 1. This quantity will be less. Think about the n is pretty large in this case. Yeah, otherwise your bound is vectors. Yeah. Right.
Yeah, that's.
So let me show you some examples. Basically, this algorithm is general enough such that when you apply this to some special cases, you can actually get very nice results, which actually incorporates the structures of these special models. So the first model is this nonlinear sort of kernel regulator, where we just assume that you have some deterministic function f star that maps from state action pair to the next state corrupted by some Gaussian noise. So of course, f star is unknown, but let's assume that this guy lives in some reproducing kernel Hilbert space where the kernel is defined as the inner product between these two features, right? Phi is the known feature in this case. So in this case, we can refine the ratio-based coverage to this relative condition number style coverage. So here in the numerator, you have the feature covariance matrix averaged over the state action distributions induced by the policy you care about. And in the denominator, you have the feature covariance matrix corresponding to the offline distribution. And in some sense, we are measuring coverage in terms of subspace rather than density ratio anymore. Another example that I like I really like is the low rank MDPs. Let me just spend maybe 1 minute talking about the low rank MDPs. So in this low rank MDP, let's see we have this transition matrix, which is indexed by state action pair and the next state, S prime. So we have this big matrix where every entry in this matrix is the probability of transiting to S prime given SA, right? And this could be a very large matrix when you're looking at large MDPs. What I'm going to assume here is that this matrix has rank D, where D is significantly smaller than the number of state and action pairs. So this factorization looks like that. And put it in a different way, you can just assume you have mu star and phi star, two mappings, such that for every state action next state triple, you can write the probability of transiting to S prime at SA as the inner product between these two vectors, right? And the dimension of these two vectors are D, which is the rank of the matrix. So in low rank MDP, neither mu star nor phi star is known, right? So for those of you who heard about linear MDP, this is really different in the sense that phi star here is unknown, where linear MDP assumes low rankness and also phi star being known, right? Which will really allow you to do sort of use linear regression techniques to solve an RL problem. Here, you just can't really use a linear regression technique, right? Because you don't know phi star, right? I'm going to set up two function classes in this case because neither mu star nor phi star known. So I'm just going to assume I have two function classes, gamma and phi, and both they capture mu star and phi star respectively. Right. So this is the realizability assumption. And in this case, my coverage condition can be reduced to, again, the relative condition number. But in this case, the relative condition number will be defined using the ground truth feature phi star, which is unknown. Right. And then in terms of the performance gap, we will get a suboptimality gap that looks like that. So we will have log of the size of two function classes in this case, because we have two, we started with two function class, and we have this D, which is the rank of the matrix. Right. So here, if you recall the algorithm, the first step is running MLE. So in that step, we are really trying to solve a nonlinear function, sort of a nonlinear function approximation, like a non-convex optimization problem.
So you say the cap P and when it's low rank, we know it's just a low dimensional like affine space. Like it's a low dimensional subspace, a linear subspace. Like in this, so it's like a two D-dimensional subspaces. So for that, can you? So I'm trying to figure out how you get the cardinality for these two linear subspaces. Then you go to the next slide. So you have the cardinality of those two functions. Yes, the function spaces are continuous spaces.
No, so here I'm just still assuming these two function classes are discrete.
The number of subspaces considered is finite.
Yeah, I'm just looking at the finite function classes, and I'm waiting to pay the log of the size of the function classes. Now, of course, in worst case, these probably will scale with respect to the number of states, right? But I'm just assuming that I have good inductive bias in my function class, and I'm waiting to pay log of the size of the function class. So, like, all we're doing here is MLE, and all we need is the standard supervised learning style generalization value for MLE. So you can literally just replace this part.
But just kind of for a low dimensional space.
Right. I'm not going to talk about the other models, but this framework actually works for several other interesting models like linear mixture MDPs and also factored MDPs. Right. So now let me briefly talk about imitation learning. So this is a setting where you don't have reward function anymore, right? So this is a setting where specifying the reward function that try to quantify the long-term behavior is really hard. Think about those robotics problems, right? Writing down the reward function is not easy, but you potentially can ask some human expert to provide demonstration. So this is the setting that we're going to look at. You can also call this inverse reinforcement learning if you want. So this is the typical imitation learning setting. You often start with an expert demonstration, and you do data collection, and you train a policy using that expert demonstration, and you deploy this policy. Right? A very famous algorithm is called behavior cloning, and people actually use that, to train self-driving cars back in 1989. So CMU did that. At 1989, they trained a self-driving car trunk using this behavior cloning, and they actually drove the car from Pittsburgh to West Coast. It was a New York paper at 1989. And the policy is a neural network. Okay, of course, you're going to have covariance shift in imitation learning as well, right? So this was the example that we saw. You're going to have running into situations like that. But imagine this case, I have a bunch of imperfect but offline demonstrations from maybe non-expert drivers, right? I could have different people driving the car around this track, but they're not racing expert. Right? But maybe I can use these data sets to learn how to actually recover from mistakes. And this is what we're going to do. So the setting is that we have lots of offline data, but we only have very few high quality demonstrations. So in this robotics control case, maybe I have a lot of offline data of this robot doing very similar tasks. These are cheap, I log them. But for today's task, I may gonna ask some experienced expert to come into my lab and provide a few demonstrations. Experienced expert is expensive. They probably have a lot of other things they want to do. So train this high quality demonstrations is not that cheap, right? So can we combine these two sources together to learn a good policy to control this robot? And again, I don't have reward function, right? It's not very easy to write down the reward function to control this robot. Okay, so the framework looks like that. I have two sources of data. The offline data might not be perfect. I have expert demonstrations, perfect, but I only have very few of them, right? And I want to design an approach that takes these two sources of data set, its input and output a policy that potentially can work well when I deploy them in the real world. So let's zoom into this box. So inside this box, I have two procedures. The first procedure is still the model-based training. So in this case, I'm going to use the offline data to train a model together with some sort of uncertainty quantification. So this p hat is the estimated model, and sigma is some uncertainty quantification, which basically says that for every state action pair, the deviation between the learned model and the ground truth is upper bounded by the sigma. So in this, if you use Gaussian process in this case, sigma probably is the epistemic uncertainty. Right? So we're going to assume we have these two pieces of information from the model training part. And once we have that, we're going to start using the expert demonstrations, and we're trying to do some sort of inverse reinforcement learning. And the way we're going to do this is to do this min-max procedure. Right? So this looks a little bit complicated, but let's pass each term one by one. So here, f, think about them as a discriminators, right? And in inverse RL literature, people also call them cost functions. So the discriminator is trying to distinguish the distribution of our policy and the distribution of the expert policy. So this is literally some sort of modification of integral probability metric between two distributions, right? And here, the expectation, the first expectation is inside the learned model p hat. Remember, I don't have online access, right? All I can trust is the model that I trained. But my model could be terribly wrong on the places where I don't have too much data. So what we're going to do is add a little bit of penalty inside this discriminator function. So if you think about discriminator f as sort of cost that you're learning along the way when you're solving this min-max procedure, then this sigma just looks like a penalty. I'm basically telling the learner that you should not go to those regions where this penalty is large, right? Because these regions corresponding to the part of the state space where you don't have too much offline data. You should focus yourself under the region where you have data and try just to do your best to mimic the expert there. That's sort of the intuition. And picture-wise, let's see I have this 2D space, and this green region contains the offline data. So outside of this green region, I have high uncertainty. I can't really trust the model at all, so I shouldn't really try to imitate the expert, for instance. But inside this green region, these are good region. I can trust my model. So in the ideal case, if my expert distribution falls into this region, then I can really use this offline data to do better than just a simple behavior cloning algorithm, because I can actually trust the model and use the model to figure out how to correct my mistake whenever I deviate from the expert demonstrations, right? I can pull myself back to the expert demonstration using this model. But in the worst case, when the expert distribution is outside of this offline data, there's literally not that much we can do except just running very traditional, behavior cloning algorithm in this case. Right? So let's look at how this works. So we apply this approach to sort of control this simulated humanoid robot to walk as fast as possible. So we have expert performance, which is a really good expert, can actually make the robot run as fast as possible. And we collected a very few demonstrations, maybe just 1 or 2 trajectories. And in this case, if you just run behavior cloning, the very classic imitation learning algorithm on these very few demonstrations, you get a pretty bad policy. And from this video perspective, it's just a policy that doesn't even know how to make the robot stand. Right? And another case is that after we collected a bunch of offline data, let's just treat the offline data as if we're like a very high quality expert data. Let's just combine the 2 sources of data together and train behavior cloning in this case. So this do a little bit better. So from this video point, it learns sort of stand and take 1 step and then falls down. But when you combine these 2 sources together using the approach that we were describing, you can actually learn a policy that makes the robot moving forward as fast as possible. This weird behavior is due to the expert policy. The expert policy is only optimized to move the robot forward in time. It's not penalizing these weird behaviors. Right? Okay, so let me summarize what I talked about. So in this talk, I was really emphasizing 2 sort of properties for offline reinforcement learning. The first one is generalization. The second one is robustness. In terms of generalization, as I was saying, we want to sort of do offline RL as if we were doing supervised learning, in the sense that we learn with rich function approximation, and we want to generalize using rich function approximation. And then the robustness is that when we have insufficient coverage from the offline data, we should hope that our approach can learn to compete against the best policy that could be covered by the offline data. So that's it. I'm happy to take any questions. Thank you.
Time for the questions.
Can you talk a little about the difficulty of optimizing for the low rank MDP and the constrained optimization problem?
Yeah, it's very hard. So for this framework, I don't even know how to really optimize the tabular MDP. Unless I factorize my constraint to be this like rectangular based constraint, like I factorize the total variation distance average over the training data to like each state action pair. Then I can run like extended evaluation. But yeah, very good question. I was just thinking about it, how to do this even for tabular MDP. I have no idea at this moment. Yeah, so this is not really a computationally efficient algorithm. I think it's interesting to see like what we can do for computation.
It's the same question, but then so how did you get the video running? This is an intractable problem. How did you approximate them?
Yeah, so that part is the imitation learning. That part is the imitation learning part.
You're still on max over F.
No, yeah, so there's a max over F. What we do is solving this min-max problem by computing best response over F. So the F in this case is just linear functions on some predefined curve. So this IPM in this case is just MMD. So you do have closed form solution for computing F. Right? And then you do policy gradient on the policy part. So that's what we did. And then we run some natural policy gradient to minimize pi. So you do small update on pi, but you compute best response for the distributed. And the model is trained by Gaussian process. So you have this, actually the model is trained by example of neural nets, where the uncertainty quantification is the distributed over the neural nets.
You said you weren't going to talk about lower bounds, but I'm like curious how hard this problem is. Like, what is known for the lower bound perspective? On the
yeah, so most of the lower bounds in offline RL is for model free side. So imagine you ask the question that I want to do policy evaluation, and I have some offline data that actually covers the entire state space, meaning that the density ratio between the policy you want to evaluate and the ground truth, sorry, the offline distribution is bounded. And you just assume realizability in the sense that your function class contains the Q pi you want to estimate. You still can't do it. You need additional function. So realizability in this case is not enough, even if you have full coverage. Similar things hold for linear case. when your QPy is linear and your offline data actually has coverage in terms of the eigenvalues of the covariance matrix, this is still not enough. What I'm trying to say here is that realizability in model-based case is actually enough. But of course, assuming realizability in model class is stronger than assuming realizability in the Q function class. Right?
So can I think of imitation learning as necessarily having a behavioral policy and also using star essentially as the expert essentially use the optimal policy?
Yeah, so yeah, you can think about this way, but like in this framework or in general imitation learning, you don't really have to sort of think about expert as the global optimal policy. Yeah. So your goal is also different, right? You just want to do as good as the expert. Your goal is to not compute optimal policy.
I guess my question was like, is there a point in selecting an expert that will be close to the one that was maximizing the previous things that we showed about the Covariate dimension, for example, rather than like, are you assuming expert as being completely exogenous, or can we select essentially expert to be someone who is going to give us a useful information about the space that we have seen?
So you're asking whether like the expert and the behavior policy are they the same?
On whether I can target my expert to be close to my behavioral policy in order to observe.
Yeah, I think the goal is a little bit different for these two policies. The behavior policy, you want to hope that it's diverse as possible. So the behavior policy could be terrible, right? But the expert policy, there you sort of hoping that it's actually doing the correct thing, like because you're trying to match the distribution of that guy. So you wanted that distribution actually achieve good expected reward. So the role of the offline behavior policy is to help you to do some exploration.
I have a quick question. For the first step we are when you're doing the max likelihood estimation, right? Is that a crucial or any kind of estimation method?
Yeah, you can do those min-max approach, for instance. So when I do the maximum likelihood estimation, I'm really just using the total variation distance-based generalization bound. But you don't have to. If you have a discriminator class, you can do min-max, right? You're just trying to train a model such that some sort of divergence, like IPM divergence, is but you need to make sure somehow your discriminator class is rich enough to capture potential value functions that you could run into in the future. Right? Because you're really going to evaluate your model together with some value function. Right?
Let's take the questions plan. It's the last talk, so before concluding, I'd like to thank our videographer, Omid Star, for helping the and some staff Ashley Hudson, Elizabeth Young, and Kellan in Finland, especially Ashley was responsible for us, and she has been phenomenal in all aspects. And the speakers.